This continues our lecture on section 3.5. This is our second lecture on 3.5, and we're going to be showing how the slope is a constant rate of change, and how being a rate of change is exactly what slope visually is accounting for. Plus, we're going to make that relationship to the addition of the slopes that I've shown once before in our classes. So the relationship between these two is consecutive points versus non-consecutive points. So let's take all these points that lie on this line here. If I look at this point to this point, I see I'm going to rise 1, 2, 3, and I'm going to run 2. And then I'm going to rise 1, 2, 3, and I'm going to run 2. And I'm going to rise 1, 2, 3, and I'm going to run 2. And rise 1, 2, 3, and I'm going to run 2. So every time we see we have that constant rate of change from one point to another, we get that constant rate of change. Well, as it turns out, I could do the same thing and show the additive property. To get from this first point to this third point up here, I would rise 1, 2, 3, and then another 1, 2, 3. So I've risen a total of 6 this time, and I run a 1, 2, and then another 1, 2, giving me a total of 4. And you'll notice that 6 over 4 is indeed the same as 3 over 2. And we could show that all the way up the number line, including this last one, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 over 1, 2, 3, 4, 5, 6, 7, 8. And so if we show 12 over 8, we divide both of those by 4, and voila, we get 3 halves again. So those the slope is either the 3 halves or the additive property, which gets us from one point to one that's quite a few beyond the next consecutive point. Now, the way that that relates to the idea in a rate of change is that we could say with a rate of change, instead of representing this as 3 halves, we're going to turn it into a decimal. So 3 divided by 2, which is 1.5. So what we have here is it's 1.5, and that's dependent units, and that's 2, 1 single independent unit. So what we see when we look at that is that over here on the graph, what we do is we'd rise 1.5 and we'd go over 1. And you see that smack dab on that line. So the idea of a rate of change is just for 1 unit increments on our x-axis, rather than being consistent x's and y's. We're only looking at just the x's. So let's go down and take a look at what I've written here about that and the different ways I've shown it. So first we wanted to notice that the slope between the lowest 2 points is 3 halves. The slope between the second and the thirds is 3 halves, and the first and the third is 6/4, which means that we have 3 halves. That's where the additive property comes in, right? Because we added 3 plus 3 to get 6, and 2 plus 2 to get the 4. And then the slope between any 2 points is 3 halves. And then the fact that the slope between the first point and the red point was 1.5 to 1, which is equivalent to 3 halves. And then noticing that 3 divided by 2 is 1.5, which is a unit rate that's equivalent to slope. So what we've seen is that this unit rate that is equivalent to our slope, that's what rate of change is in the first place. And the rate of change on a line is always constant. Now, looking here, what we're seeing is that additive property. And we're seeing it in a different way, because the ordered pairs, if I take that coordinate system above there to be 0, 0 in my lower left-hand corner, I have my first ordered pair at 0, 2. And then if I add 2 to that, I get my next x coordinate, and if I add 3 to that, I get my next y coordinate. And that is this y and the x is adding. So here's 0, 2. If I add 2 to that, then I get the value for the x coordinate of the next one. And 2, if I add 3 to that, I get the y coordinate of this next ordered pair. And that's the additive property of slopes in